Okay, so thank you all for coming. It was of a great pleasure to be invited to give a rant about RDF. So some thank yous, first of all. Thank you to Don Waters of Mellon for initially inviting me to present the upsides and downsides of RDF last year, and to Cliff Lynch of CNI for inviting me to give a more detailed presentation here. And in chronological order, thank you to Herbert for the shout out in the keynote this morning. Okay, so what I want to talk about in this session is graphs and how they are both good and create problems for us. The wide open world that RDF throws us into, ontologies and identities when they are good for us and when they provide challenges, serializations and technologies, linked data, of course, time-based issues, and you've already had the background of that from Herbert. And yeah, blink tag, warning, controversy will be within this presentation. I'm sure that you will not agree with everything. That's entirely intentional, and I hope that it makes for some good discussion and questions at the end. Okay, RDF, then linked data and semantic web. Oh my. So it was a really great idea when Eric Miller and Dan Brickley came to me in about 2003 at a conference in Europe and said, "Hey Rob, have you heard about this cool thing, RDF, that we're working on? And it's going to be the semantic web, and all of the computers are going to understand everything, and it's going to be Skynet, and it's this fantastic idea." That was back in 2003, and it's still a great idea now in 2013, 10 years later, but it hasn't really materialized as Dan and Eric had hoped for 10 years ago. And there has been a lot of progress made. I'm not saying that we're still back in the very, very early days. But there's still a lot of challenges left to solve, and a lot of area that needs more research, more exploration. So some things that this talk is not, rather than saying what it is. It's not an introduction to RDF, but I will try to go through all of the challenges in a way that if you're not RDF experts, then you'll still understand what the problem is and are you going to face it in your everyday life. It's not an advertisement for linked data or an apology for the non-existence of the semantic web. We've had quite enough of them, thank you very much. I'd rather present something which is a little bit more balanced rather than just an infomercial. Okay, so the first topic is, of course, graphs. So RDF is a graph structure underneath. You have these triples that connect resources all together, and you end up with something that looks like that diagram of skittles, where there's some yellow skittles and some red skittles and some orange skittles, and little lines of thread that link them together. So this is great for modeling reality, because reality isn't just a tree. It's not just a very hierarchical, structured thing. It's this big mix of interrelationships between objects, people, things, concepts, and so on. At the basics, a tree really is a graph, actually. So XML, for example, or Mark, or any of your other favorite formats that have structure, are a tree that has a root node and then relationships coming down. That's just a very, very simple form of a graph. So it's not that you aren't using graphs, it's just that you don't know it. The nice thing about RDF, and we'll come to the ways that this works, is that new information can quite easily be inferred from the graph, both with the information, the data in it, and from the structure of the graph. So, for example, there's a lot of work being done in bioinformatics to determine, this gene activates this gene or that sort of thing, so that you can then say, well, if we do this, we know from extracting all of that information, putting it into a graph, that all of these processes will happen, a workflow in biological terms, and we will end up with this result. So that can be fantastic for in silico science that Herbert briefly mentioned in his presentation earlier. The next thing is, of course, that increasingly interesting questions can be asked if you have the graph structure. So instead of just having, what is the author of this book, you can say, who did this author co-author with? Or who wrote about bioinformatics co-authored with people who also wrote about digital humanities. Right? That you really cannot do with a traditional tree-based structure. You need those interrelationships between resources in order to ask and answer those sorts of questions. And finally, in comparison with XML, which I guess everyone is familiar with, you don't end up in this sort of semantics and syntax hell of having to take a real-world representation, which is messy, and somehow smash it into this tree structure, which is very hierarchical and very fixed. So you can quite easily and very accurately describe the situation without having to make concessions in order to use a particular format. Okay, so those are the good things. This is why I really do love RDF. However, it becomes much more complicated to do things with it afterwards. So querying becomes much more complicated. And all of these issues about graphs are really linked to the fact that both the structure of the graph and the data within the graph are important. If you have a link between in a social network between two people, so person A is friends with person B, is friends with person C, and so on, then that structure is of interest, not just the people themselves, not the people individually. And that's not true of most other systems. The problem that RDF currently has, or the tools that work with RDF, is that the data within the graph is currently treated as a second-class citizen compared to the structure, because that's the new, interesting, exciting research topics. So, for example, if you had a full text of a work and it was encoded in RDF, it would be very hard to do full-text search, because that's not what the tools are designed to do. They're designed to traverse the graph and look at the structure, look at the links. Compared to, say, XML, PDF, plain text, where only the data exists, and of course that's only what the tools look at. So in that case, full text is much, much easier. So if you look at it, the equivalent queries between Sparkle, the standard for querying RDF, and I'll give a prize to anyone who still recognizes CCL from Z3950, you can see that the graph query, you have to know the structure in advance in order to do the query. You need to know that there is such a thing as a book, and it has a property, a relationship called creator, and that's going to be to a person, and that person has a name. You can't just do AU:Sanderson to find books authored by someone with the name Sanderson. You need to understand the structure of the graph in order to do the query. This is an issue for front-end systems. If you expect a user to type in that, then yeah, you shouldn't be using RDF. Because all the user is going to do is type in at most Sanderson and, at least Sanderson and at most, I think about this person as an author. Of course, the front-end system shouldn't do that, and there's mediating ways of fixing that. But the overall problem is the graph structure makes querying more complex. It also makes the serialization and storage more complicated. So graphs don't have a start and an end. It's this big amorphous blob, relationships going everywhere. So there's no obvious place to start when you want to come to write that graph out. And with a tree, with the XML, you start at the top node, you work your way down, you come to the last node, end. In a graph, not so easy. Also, you don't want to end up repeating yourself, and graphs can be cyclic. You can have a link from one node in the graph to a node which is also referenced by somewhere else. So you need to have links within the graph without repeating the information. They also might point outside of the graph to resources that aren't described, and you need to be able to understand the distinction between those two. This then plays a role with storage of RDF and of graphs. So it will come to this, but all assertions in RDF are of a global scope. So the triple stores, the technology that is used for storing RDF, simply stores them in one big lump. There is a big bucket, all of these assertions go into it. That's okay, it's great for inferencing, it's great for finding those unexpected connections. However, it makes it very difficult to get it back out again, because you don't know, here is my document, I put it in, and bam, your document's gone. It's just triples in this big bucket. Secondly, the storage system also has this issue of structure and data, not just data. So if you have had issues with content management systems failing to do the right thing with XML, where it's just a blob of data, imagine the troubles that you have with triple stores, where it also has to worry about this complicated graph structure. And the third point, still about structure and data for graphs, is that visualization is really hard to get right. It's to the point where you don't even know that you've got it right when it is right, unless it's very, very swish. So documents are pretty easy to visualize. We have web browsers, we have Acrobat or other PDF viewers and image viewers and so on, where there's a bounded set of information that needs to be presented in a way that somehow represents a physical structure. Data, we're getting there. There's Many Eyes, which is an online visualization system. There's lots of increasingly valuable time series analysis and charting software for visualizing the underlying information of science. But graph visualization is pretty much exclusively terrible. There is very, very few instances where it's done right. So this is the Facebook graph from 2010 of international friendship relationships. And this, I would say, is a graph done right. You can see, for example, I'm from New Zealand in the bottom corner there, and this is probably a bug, but there seems to be a lot of friendship relationships between New Zealand and Australia. Okay, so here it's easy to see what's going on, and it encodes both the real world and the graph structure pretty nicely. That same sort of information could and often is visualized in this sort of way, where you can't see, and that's the problem, any of those little node icons which are labels for people, or any of the interrelationships between them. Right? It's just this big gray and blue mess. But unfortunately, that's what we often get presented with in graphs. So to summarize then for graphs, they're very powerful, but they become complicated to work with. You can have a very accurate modeling of reality, but with that accuracy comes great responsibility. And you need to have the systems in place in order to do the querying and the processing, the visualization of those graphs. There are some mitigating factors. The software libraries are really coming along, and they can manage the complexity pretty well. In 2005 or so, a triple store that could hold 1 million triples was cutting edge. Now it's in the billions, if not trillions, which is more than most individual projects would ever need. And also, there's an increasing tendency towards treating part of the graph as a document, so putting it into a regular XML or JSON or other database system, and also ingesting that same information into the triple store so that you can do this inferencing to discover new knowledge. So it's really like having your cake, e.g. looking after it as a document, and eating it, e.g. treating it as a graph. So the takeaway here for graphs is that really other structures don't get complicated because they don't have the expressiveness that a graph can provide. If you need the expressiveness of a graph, or you can use it, fantastic. If you don't go there. Okay, so then one of the interesting decisions in RDF, and made for a very good reason, is that there is a single global scale graph that everything is part of. So every triple exists by itself, every statement, and they're all in one big melting pot. There's this theoretical great triple store in the sky that if you had all of them in one system, you could have all of the world's knowledge. That doesn't exist and probably never will, but that's the theory. This is why it's a great idea, and underline great and underline idea. So it's great for data reuse. You can simply pull the stuff out of the big triple store in the sky and use it. You get all of the richness of data across multiple sources, all these different institutions contributing to this one pool of knowledge. That sounds fantastic. Anyone can make assertions about anything. You don't have to control the thing. You don't have to own it. So if you have a scholar working on a particular resource, they can make assertions about it. They can contribute their knowledge to the common good. The identities are global, so there's an identity for that scholar within the system. There's an identity for the concept that they're working on. And it's distributed. You can incrementally add to other people's descriptions. So if one scholar says A, and other scholar says, oh, that's great, and I can also assert B about this resource. So it's really taking data and applying the architecture and thoughts behind the World Wide Web, where anyone can link to anything, describe anything, talk about anything. All right, so those are the good things. Here's something that you need to understand before I go on to the trouble. So in RDF, it's an open world assumption, which means that if something is not stated, then it's not false, it's unknown. So for example, you have the statement, grass has the color green, grass is green. You then ask that trivial knowledge system, is grass red? Is the color of grass this thing that I understand as red? In a closed world system, the answer is no, because you know that grass has the color green. In an open world system, the answer is I don't know. It could be red. All I know is that it is green, but it could also be red at the same time. So this gets us into a lot of headaches. So here's the positive use case taken from Open Annotation, which is a RDF-based annotation system that I work on in the W3C. So someone, let's call him John, publishes an annotation about part of a web page. So you have the annotation, the comment, a segment of the web page which has its own identity. It refers to the web page as a whole, and it has something that describes where that part is within the web page, and that's that green location bubble. So now someone, we can call him Brewster, comes along and archives the page. Now Brewster can say, I took this page at this time and I archived it. And he can attach it to that segment node without John's understanding, knowledge, awareness, permission. He points to a state which says, here it is in the archive, and you could use Memento to then point it back to say, this web page has this archived copy. So that's great. John doesn't need to be aware of the archiving, Brewster doesn't need to be aware of the annotation, but everything slots together perfectly. All right, so keep this in mind. Right, let's turn it around a little. What happens if we have someone, we'll call them Fred, who instead of taking the annotation and archiving the web resource, say that's already happened, but he then comes along and makes an assertion to say, It's not about this web page which is archived, it's about this part of this web page, which is really changing the fundamental meaning of the annotation. If you said, I like this thing, this, say, a book, I like Alice in Wonderland, done. That's your annotation. And then Brewster comes along and archives Alice in Wonderland. Fantastic. Now Fred comes along and says, oh no, we're going to change what the understanding of this segment is to say it's this part of Alice in Wonderland. And maybe you don't like that bit. Maybe you think that bit's terrible. But it's not under your control to prevent Fred from saying that. So the next issue with the open world assumption is that every assertion is considered to be true in all contexts. There's no conditional asserting of things. So the easy one, and this trips everyone up, myself included, is lists, ordering. So so this is from Shared Canvas, a project that I work on with Tom Kramer at Stanford. And Shared Canvas is about digital facsimiles of medieval manuscripts. So these canvases, the rectangles, represent pages of a medieval manuscript. So what we want to say, of course, for a page-turning system, is that Canvas 1 comes before Canvas 2, comes before Canvas 3, comes before page 4, page 5, and so on. Right? So how do you think you would do that? Right? Well, it's relationships, right? You just have a relationship to say that Canvas 1 has next page Canvas 2, has next page Canvas 3. Right? No, wrong. Because anyone can say anything, and it's a global statement, and you can't prevent anyone from saying it, and it's unknown if you don't say it, right? So what happens when someone comes along and says, okay, Canvas 1 is next to Canvas B? Right, now it's no longer a list, now you've got a graph, and your page turning system is going to have a world of hurt. And there's very good reasons why you might want to do this, especially in medieval manuscripts where they get rebound all the time and the page order changes. Right? So if Jane has one order in mind when she's making her assertions and Freya has a different order in mind when she's making hers, they could both be correct in their own context. Right? So this is a problem. The locality of information does need to be possible. So to talk about one of the projects that I was involved with Herbert on, ORE, we have a notion of a proxy, which stands for the resource in the context of the aggregation, in the context of the book. So we could say that there is a proxy for Canvas 1, and it stands for Canvas 1 in the context of this particular sequence, and in that context, we have this next link to the next proxy, next link to the proxy for the third page. So now we've introduced, as all computer scientists know, any problem is solved by adding a layer of indirection. And this is one case when that's not only a nice stereotype, it actually does work. However, it's very expensive because you have to mint identities for all of these little guys. So in Shared Canvas, we use an RDF list construction, which is taken care of by the libraries. It's taken care of in the serialization. You never actually see it, but the triple stores underneath are going to mint a whole bunch of these little blank nodes. So they don't have any identity. They're very simple. They're very similar to proxies, but they don't cost you anything. You do not have to mint a URI just to have a blank node to have a list. The reason that ORE has proxies is that there are more things than just order that we want to say about the resource in the context of the aggregation. And then you do need identity. Okay, so that's the open world. We have the single global graph that everyone contributes to, so it's not just here is my knowledge which I can work with and infer stuff from. It's everyone's knowledge. It is the common good, and it would be Skynet if it actually existed in reality. The problems are that it makes local constructions where context is important as opposed to the global context. It makes them much more complex and more expensive to deal with. So if you need to have order, and that is your primary thing, your primary structure that you need to encode, then maybe RDF is not for you. If you don't have order of things, or it's not the primary thing, and you do have good relationships between resources, then it could be useful. The second point that I made was that remote assertions can change the understanding of the identity of things. So John saying, hey, it was actually this part of the book that this other person was talking about, is a problem, but one of the mitigating factors is that trust is required in all data. If you're going to consume stuff off the web and trust it, then you get what you're asking for. There's going to be a lot of complexity, a lot of misunderstandings, a lot of spam in the future, where people are saying, well, hey, this resource has a homepage to Viagra.com, or so on. It makes it harder to take shortcuts. So you have to introduce these local identities for local things. I would argue that that's actually a good thing. It forces you to take into account that you do have a context. You have to think about it. It's more expensive, but at the end of the day, hopefully, you'll get the benefits from doing it. And finally, some grass really is red, especially in New Mexico. Well, kind of brown or dead, but there you go. And in theory, it could be both red and green at the same time. Right? So, yes, maybe grass is normally green, but that's a particular context. Right, on to ontologies and identities. So ontologies are collections of relationships, named and described and identified relationships between things. So for example, you could know that DC title means label or name, and nothing to do with a property title or title for a person. And that's very well described in the ontology document that defines those things. Each of those things has a URI, so they can be unambiguously reused anywhere in the world. This reuse of semantics then makes it much easier to build applications that use those semantics, either for visualization, for inferencing data, and so on. Because the relationships have URIs for their identity, it means that anyone can develop their own ontologies independently without having the namespace problem that schema.org, for example, does have. So if you want to say that name means something or title means something, you need to get permission from the big three, Google, Yahoo, Microsoft, to say that in schema.org name means this. However, in RDF, you don't. If you have a particular need, a niche, and you have an ontology, you can make those assertions and it's true. If other people don't use your ontology, that's not hurting you. If they do, everyone wins. So those were the relationships between things in the graph. Also the nodes in the graph, the person and the book, they also are identified by URIs. That means that everything has a globally unique identity. It also means that, hopefully, when people reuse those URIs, so if there's for example, DBpedia is a version of Wikipedia, but in RDF. So it's a machine processable encyclopedia. So if you reuse those DBpedia URIs for things, and everyone does that, then all of the knowledge really does glue together. And that's when you get the benefit of everyone contributing to this single global graph. So as someone who's worked in standards for 15 years or so, I really love this XKCD comic. Because the nice thing, and to paraphrase another aphorism, the nice thing about ontologies, normally standards, is that there's so many to choose from. Right, so because some people, because you can make up an ontology to fill your particular niche, you can, and people do. In fact, everyone does. The amount of reuse in the linked data web at the moment is appallingly low. There's no hard statistics because no one knows exactly how many ontologies there are, But there are many, many instances of, for example, descriptions of books. And even if you did find all of them, you then have to make a choice. Which one is the right one for me? Which one is the one that's going to be used by other people, be used by applications, so that then I don't have to reinvent the page-turning wheel, for example. And if you find something that's almost right, but not quite, do you just use it and hope that it works out, and that these page-turning things, for example, actually turn the page even though it's a scroll and you have to wind the pages? Or do you then create a new ontology and specialize it to say, this is exactly what I mean. I mean that this is a bit of space which, if you turn these things in the user interface, then the scroll moves along. So, for example, maybe I'm being slightly harsh on BibFrame, but as they're the newest in the bunch, they get to be the 15th in ontology for describing books. There is many. Dublin Core has 2, Prism, SDL, Sweato, DBLP, and so on and so on and so on. And the same applies to identities, for very good reason. There's lots of identities for the same thing, and it's hard to find the right one that's going to be used. It's a guessing game. Is this identity, is this URI going to be picked up by other people or not? So identity can also have a contextual component. Los Alamos has an identifier for Oppenheimer, but does that differ from what is meant by the identity for Oppenheimer in DBpedia? We have a lot more information about him than DBpedia does. We might want to say things about Oppenheimer and given his work within the lab that we would certainly not want to then leak out via a link from DBpedia. So there is context to identity. It's a case of knowing when to mint a new identifier and when to use the existing one, and that's tricky. So shared ontologies can increase interoperability. It means that you don't have to rewrite code that everyone else has already written. Shared identifiers will mean that the graph merges so that you get this new knowledge. So those are the great things. And the problem is that there's lots of them. So that makes it harder for the graph to merge and makes interoperability harder. There are some mitigating factors here. You can also assert the exact equivalence between identifiers, between URIs. So you can say that, for example, the identifier that the lab has for Oppenheimer is the same as the identifier that DBpedia has for Oppenheimer, and then all of the systems will collapse those two resources and associate all the information together into one big blob. And that's just another triple that you put into the data set. So that's easy, actually. That helps an awful lot. It means that you can use the same parsers. It means you can use the same creation tools. You have the same trust mechanisms to say, do I trust the fact that Oppenheimer is Oppenheimer, or do I trust the assertion that CNN is Viagra? Probably not for the second one. There are also well-known ontologies and identifier schemes. There's, I forget the site off the top of my head, but there is essentially a ranking table for ontologies that says, this is how many times it's used compared to these other ones. And as the graph continues to increase, as more and more people contribute to it, then winners will become obvious. There's always competing standards at the beginning, and this is really the beginning. Okay, serializations. So I'm afraid I struggled with this slide, I have to admit. I really don't have very much good to say about serializations of RDF. In fact, the only thing that I could come up with is that the new JSON-based linked data format is actually pretty good. It encodes the graph, and it looks like what you would expect JSON to look like. And that's not true for any of the other serializations. So RDF XML has been described by Manu Sporny as the semantic web's 3 Mile Island incident. I think that's a great description for many reasons. So RDF XML is a disaster. It's trying to cram a graph structure, which is messy and complex, into a tree structure that's highly structured and not complex. Of course it's not going to work. It doesn't look like XML because you have these little itsy bitsy chunks of XML. It doesn't look like a graph. It's very verbose. So essentially, it's the worst possible combination of technologies. The second issue is that there are way too many of them. There's probably 10 or 12 serializations for RDF because someone comes up with a great new 3-character saving serialization or something that's slightly easier given some other system. So this means that then you need to have multiple serializations for interoperability. And not every system will implement all of those serializations, and then you have interoperability hell. Right? You don't know what you're going to get when you go and ask for the description, and then you have to hope that your library can understand what you get back. That's a disaster in anyone's books. And this then leaves room for competing systems such as schema.org, microdata, and so on, which say, well, we only have one serialization, and it's just HTML. Isn't that great? Yes. If RDF only had one serialization, and it was a good graph-based one, then it would be able to compete much more strongly with schema. So JSON-LD is my only thumbs up on serializations, but is it just the 15th serialization? Is it the one serialization that takes all the previous ones and adds a little bit more? And yeah, practically everything else sucks about serializing RDF. There are software libraries for most of the common languages, Java, Python, Ruby, C, etc., but they're not consistent in exactly what they implement. Okay, platform technologies then. So this is something. This is my happy slide. The technologies that underlie these systems for RDF and for inferencing are rapidly improving at the moment. And there was a period where it was kind of spinning up, but now it's in that hype, the upward part of the hype curve. And there's open source, there's commercial systems, there's open source with support, there's commercial with support, etc., etc. They have vastly improved scalability over the early systems. So if you looked at it 5 years ago and thought, oh no, we have, that none of the stuff will let me do what I want to do, I would encourage you to look again. Things like forStore, shard across multiple machines, don't have vast memory requirements, and do everything blazingly fast. There are cross-platform APIs coming out where you have a single method that you can talk to multiple systems. So you write your client code once, and if you don't like forStore and you then want to use Neo4j or Allegrograph or you can swap out your backend without having to rewrite the entire stack. So that is the sign of, in my opinion, a maturing technology stack. It's in use in many of the Fortune 500 companies internally for business intelligence. If you have this graph of customers and products and prices and so on, and you can create new knowledge by inferencing on it, of course you're going to do that. And externally as well. So Google Freebase is trying to be the big triple store in the sky, where they pull in all of DBpedia, all of the linked data that they can find, and make it freely available to interact with. So that's, I know lots of people love to hate Google, but that's a particularly nice project that they have. The storage systems are moving away from triple stores. In fact, I'm not sure that there are any triple stores left, and into quad stores. So the fourth point is the identity of the graph or the document from which the triple comes. This allows you to do all sorts of things in terms of trust, provenance, context, and so on. So that is the named graph issue, if you've heard of that. So that is becoming real. That's becoming supported. Also becoming real is inferencing. You know, it used to be computationally intractable. New research, new algorithms, and better machines are making it a viable option. And there are people working on user interfaces, but they still have a long way to go. So then, linked data, finally. So linked data essentially was what kickstarted the new semantic web from the great idea back in 2003. It provides practical implementation advice about what to do specifically. People have implemented it, and it seems to be growing, it seems to be working. So the advice is to give everything a URI, make them HTTP URIs. When you dereference the HTTP URI, you get back a description of the thing that's identified. That description should link to other things, which are identified by HTTP URIs that describe themselves. And those descriptions should be in RDF, XML. Okay, so ignoring the RDF XML bit. The problem, however, with linked data, there are two problems. The first is that it reuses one of the HTTP status codes, 303, which says, see also this thing. And that's a very general idea. You go over there and you'll find something. Linked data applies more semantics to that to say, when you go to a URI and you see a 303, it will take you to an RDF description of the thing which you went to in the first place. And that's a very big change. They are hijacking the meaning of the status code. And there are arguably, and if you follow any of the lists about linked data or RDF, indefinitely arguably, there are arguably unnecessary, it's unnecessary to do this. There are easier patterns that would accomplish the same thing using 200 status with content location. Secondly, the extent of description that you get back when you get that description is typically thought to be only the thing that you asked about. But that's not very useful in most cases, because it means that you then need to follow all of these links to pull back the information that you need to generate a useful system. Right? So then you end up with this HTTP storm of the system going out and dereferencing all of these things. You know, you end up with a web crawler that doesn't know when to stop because it doesn't know what you need to answer the questions because you haven't asked the questions yet. So, yeah, the follow your nose recommendation from linked data is good if we had some mechanism of synchronizing resources sensibly and effectively. What about if you want to describe things that you don't control? You know, that happens all the time. That's one of the big selling points, that anyone can make statements about things. But if you can only return the description of the thing that you have the URI for, then you can't do that anymore. And that's not good. That's one of the issues with the linked data as opposed to the underlying RDF that makes it, in my opinion, much less attractive. And finally, using HTTP headers for content negotiation is a real pain. So in Memento, we have a single HTTP header to do time-based content negotiation. It's taken years and years of knocking on doors and writing papers, implementing systems to try and get anyone to do anything with that HTTP header. But that's what the web architecture says to do, so that's what we have to do. Which brings me to temporal issues. And resources change over time. I don't need to go through all of these things because Herbert has very nicely described them. But reality changes, data changes, the ontologies change. The document web, the data web, don't really have good solutions for managing that change. We can't have new URIs for every version, and if something changes, you don't know whether those assertions still apply. And Memento and Resource Sync are hopefully going to be mitigating factors in that regard. So in summary, graphs are very powerful structures and they allow you to model reality very explicitly. The complexity that is involved with doing that can be managed by tools and software systems. So that's good news. The open world also introduces complexity, but that complexity enforces good practices for identifying things with context and not just glossing over it. And without the open world system, it would just be data on the web, as opposed to the data web. Trust is a big issue and going to be increasingly so in the coming years when spammers discover that systems can be easily hijacked by adding in new assertions. But that's true of any data. We don't ingest arbitrary stuff that we find on the web into our databases as a matter of course. There are competing ontologies, competing systems, competing identities, but winners will emerge for those as the system as a whole, as the global system matures. And JSON LD is a very strong serialization. It looks like JSON, but cleverly encodes the graph. Parsers for it exist. And people are moving reasonably rapidly, given the backlog of systems to migrate from RDF XML over to JSON LD. And I don't think it's too much of a stretch to say that good people are working on the temporal issues. So thank you very much for your attention. I'm very happy to answer any questions or attempt to that you may have.